Good evening, everybody. I hope you're all well. This evening we have David Benoit from Hull University, the University of Hull, get it the right way around. He's a senior lecturer in molecular physics and astrochemistry, and he holds a biochemistry degree from the University of Lucerne, a PhD in theoretical chemistry, and a German habilitation in theoretical chemistry. He has authored over 65 review publications and has 20 years experience in using high-performance computing to solve problems in quantum chemistry, molecular physics and astrochemistry. His research focuses on the development of highly efficient approaches to describe quantum properties of molecules in different environments, grain surface, ice inclusion, or pH changing oceans, for example. He also has a particular interest in quantum computing, astrochemistry, and astrobiology, vibration theory, biological signaling, and molecular surface interactions. So, plenty to keep him busy there. So please, can we have in a Mitzvah and Swinton way, a wave of welcome to David Benoit.
Thank you.
Well, think what a set of mad people.
Okay, David, I'll just spotlight you.
So let's see if this works. That's great.
Okay.
So I'll just assume everyone's happy and ready and that it all works, that everyone can see it. That's brilliant. So, well, first of all, I think thank you very much for sort of listening to me tonight. What I wanted to tell you, I realized I was sort of looking back through my diary and realized that I think the last time I actually came in person was 2018, I think, or some sort of roundabout then. And I thought, oh, what was I telling them about? And I think for some of you who have good memories and might remember me, I was talking to you back then about comets and chemistry and various things. And there was some idea of water. And I thought today would be sort of a good time to actually explore the theme of water a little bit more. And this time I went completely the other way to looking at ocean world. So the reason for this is that in the research that we do, so there was this big long list of all these things that we do, but more or less what we're interested in is really looking at how water influences what happens around us. At Hull, I'm also sort of running the astrobiology program. So this is really what we're trying to, I suppose, to summarize it, to look for aliens if we can, but more seriously, we're sort of trying to look at where could we imagine life taking place in the universe. And so tonight what I'm going to do is I'm going to give you a little bit of a tour around ocean worlds. We're not going to go very far. We're going to try and stay within our solar system. There's loads of other ones, but I will sort of show you I think what I found a really interesting perspective on what happens in how water is actually much more present than we think. So this doesn't work, so we'll go there. There we go. So what's an ocean world? We're going to start with an ocean world. Well, the definition of an ocean world, if we actually look it up, it's a terrestrial type planet that contains a substantial amount of water at its surface or with a subsurface ocean. And when you actually read this, you think, well, you're just describing Earth. That is what it is. We're a terrestrial planet. We've got quite a bit of water. We've been referred to as the blue planet. If you actually read, the small print, which you should always do, you find that this also says, oh, this can also be lava, ammonia, hydrocarbons, etc., etc. But we'll come back to that later. But so for essentially a very long time, most of up to the end of last century, the astronomers were thinking, well, an ocean world, there's only pretty much one it's the Earth, and we sort of know roughly how this works. So if you if I've sort of put on a hat of planetologist, so before I go into this, I'm going to do a couple of disclaimers. I am not a geologist, and I'm only a sort of part-time planetary scientist. I'm really more of a chemist that does astrochemistry. So that's sort of interesting, but we'll see sort of where that all leads, and we'll come back to chemistry eventually later on. So if we look at Earth and we look at the structure of what a planet, what ocean worlds look like, we'll have something that looks basically like this, where we'll have a core, a mantle, and essentially a crust, and in contact with this crust we'll have an ocean. Of course, on Earth we know that we're not 100% ocean, so we've got bits of soil that come up, which is basically where we live, but we'll also have in some places varying depth of ocean, varying depth of water, and overall we can sort of imagine this reasonably well, and that's fine. What happened then is suddenly in around 2000, people were looking at the Galileo mission. Some of you might remember the Galileo mission that went all around. And there's this really interesting paper that came out in 2000, where up to then people have suggested that there might be worlds or moons or planets that had oceans as well. And so what Galileo was doing there, they were taking magnetic measurements near some of the satellites of Saturn. And for those of you who have been glued to their telescopes, like I was, there's been some really nice views of Jupiter and Saturn and all these various things. So this is Jupiter, looking around Jupiter, and we had here a couple of the Galilean satellites. And so what they did is, as they were measuring the magnetic field as they were going through, these were some measurements that were already done, and they were reanalyzing those. What came out is the fact that in order to explain the magnetic measurements around Europa, it's one of the satellites, you can see Europa here on, this is a picture of the aurora on Jupiter. And in order to explain this, the only way that you could explain the influence of Europa on the magnetic field was if Europa had a planet-scale liquid ocean. So at that point, and this was then double-checked, it was already sort of suggested maybe beforehand, but this was sort of the tipping point around sort of, the millennium, where people went from a model, which is the one at the top, where it said pre-2000, which had essentially imagined that Europa looked like this, where you'd have a core, some ice that went all the way from the core to the brittle surface, to suddenly having something that's much more exciting, where we'd have a metallic core in contact with a liquid ocean under the ice, and then an ice cap. So that sort of surprised people quite a bit. Not a lot, but at the time, people were saying, well, ocean worlds is really the Earth. So now we had two ocean worlds. We had the Earth and we had Europa. And if you sort of continue this, so I tried to make a sort of rough timeline. So Europa was sort of confirmed in 2000, and then through some more of the Galileo mission, so they reanalyzed things for Ganymede, was confirmed as being also an ocean world, and Callisto as well. So these are sort of Galilean satellites of Jupiter. What we can see, what I've put then, the pizza slices that you might be able to see actually sort of are sort of cut out of what the current model for these planets are. Where here for Europa, we're imagining a core and some silicates, and then the water, and then a bit of ice. Ganymede, we'll see in a minute, is what we call a water sandwich. So we'll see that it's got ice on both sides and some water in between. Callisto is the same thing. And then things continued with, then this was the Cassini mission, where in 2012, Titan was also found to have a liquid ocean underneath some ice, and more recently in 2014, Enceladus. And that was sort of more or less the end of the Cassini mission and the data. So these were focusing more on Saturn rather than Jupiter. And right at the edge here, I've put New Horizon, which is looking at sort of Pluto and Triton and all these various things. This is data that's still being analyzed and still a little bit controversial, where people are sort of thinking, oh, could there be, maybe, maybe not. So once we've sort of worked out that there are these possible ocean worlds that exist, to give you sort of a rough idea, for example, Europa has about 2 times as much water as the Earth has by volume. So this is not a little bit of water. This is really a huge amount of water. The one that has the most, I think, which is either Callisto or Ganymede, have really something like 30 times more water than we have on Earth. So these are really huge worlds full of water. And one way of doing this, so that the way we essentially look at these and analyze and work out the data, is we make models of these things. So you start with what we call a simple icy moon structure. So this is for example Europa, which would be your sort of typical icy moon, where the idea is you really have a core, a mantle, and then a water crust that goes sort of all around. So this is a bit different from what we have on Earth. On Earth, we will have sort of the mantle that will poke through and have continents, etc. So here we have a water layer and an icy crust. Every now and again, you'll have lakes and things like that, and sort of the ice might locally crack as well. So we can see some of these cracks, is what is called this chaos terrain. You can see it on the sort of lines that you see on Europa. And the other option that you have is what we call the water sandwich. I quite like the water sandwich. Initially, I thought this should have been called an ice sandwich, because it's water sandwich between 2 things of ice. But then I sort of thought about it, and I thought, well, actually, you know, when you're having a ham sandwich, you're talking about the thing in the middle. You're not talking about the bread. So here it's really salt water that is sandwiched between 2 types of ice. This is a bit weird initially, because it looks like the ice that you have underneath is closer to the core, and the core is presumably reasonably hot. And so the idea was to say, well, how does that one work? And this is essentially something that works because if you have a larger moon, you have much larger pressure. You have an increased gravity force that is able to essentially pull your ice down and compact it to ridiculously large pressure. And so you're making what we call, for example, here tetragonal ice, which is a different type of ice that is very, very compact. And more importantly, it's essentially denser than the normal ice that we have. So what happens is it'll sink. So you essentially have a nice insulating ice bubble for your salt water to be around, and then hexagonal ice on the outside. So we can look at a lot of these various worlds and see sort of what I would call the anatomy, and see what these things look like. And these are all the results of mathematical models that people have fitted onto the observations. The thing to keep in mind when we're looking at those is, obviously, this is still reasonably new for astronomy. I mean, we're talking about, you know, a field that's more or less been created in, you know, just before the start of the millennium. So it's only been going for about 20 years plus. So things are still quite fluid, if you excuse the pun. You have a lot of things that change, but more or less, we know that sort of Europa and Enceladus have a similar structure where the water is directly in contact with a rocky silicate core here. And things like Ganymede and Titan will have a sort of water sandwich. So they've got these double ice sort of layers because they're much bigger. The weird one is Callisto. So Callisto, in sort of planetary jargon, people say that Callisto is not fully differentiated, which took me a while to understand. What do they mean? What they actually mean is that the rock and the ice at the core is not fully separated in two layers. So you have a sort of, you can imagine the core here to be sort of a mixture of sort of ice and rock. And essentially the idea is maybe given time, these might eventually separate. Another thing that's possibly interesting is I've also got here Io, which is a volcanic type satellite. But here, essentially, this is also in some ways an ocean world. Here, the difference is you've got an ocean of magma, of lava, of molten rock that is there. But you can see that the structure is a little bit different. If you solidify magma, you get rock. So this is what you get. But technically speaking, in terms of sort of modeling of these things, it's a fluid. It's not quite water. I wouldn't really want to drink it, but there you go. This is sort of roughly how this thing works. So we've now seen these ocean worlds. We see sort of roughly what their inner structure is, but where can we find them? So now here I've told you about a few of those. And what I wanted to do is sort of put them a little bit on a map. So if we actually look at the inner solar system, well, we've got Earth, which is here. There's not much, actually. We'll see Ceres a little bit, maybe. I'll talk to you a little bit later about Mars and Venus. But the first ones that start to be considered sort of confirmed ocean world will be Europa, Ganymede, and Callisto here. So these will be these ones, Jupiter satellites. So here, essentially, at this stage, we're already in what we would call the outer solar system. So we pass the asteroid belt, and here we have these ones. And as we go on there, we'll see somewhere Enceladus, there's Titan there, which would be for Saturn. We have some question marks maybe around things like Titania, Oberon. Triton looks promising as well, and we've got Pluto here, and of course at the minute New Horizons is busy sort of exploring that sort of region, so here we don't really know very much. But potentially here the interesting thing is that these ocean worlds seem, apart from Earth, to be really past the asteroid belt in what we would call the outer solar system. They all seem to be hanging around, and this might be important later, a reasonably large planet, which essentially we'll see sort of provide some sort of shielding to what's happened. And we'll see that later when we come back to what happened in the inner solar system. Great. So let's click on. So what I'm going to do now is I'm going to pick some of these worlds, and we're going to sort of have a bit of a look in more detail at each of those. So Europa was, I put it first because it was the first one that was confirmed. We can see sort of the nice sort of lines here on Europa. Europa is an interesting one. Its size is a sort of size comparison here compared to the Earth. It's not one of the biggest one, but it's usually a very, very bright white satellite. So its albedo is very, very it's about 0.6, I think, and so it's sort of more or less like a snowball essentially in terms of optical properties, and it's very, very smooth. So it has no craters, at least that people can tell, or very few, and this would be an indication of either it's extraordinarily looking, extraordinarily well shielded, but more likely what's happening is it's being probably due to the possible active ocean, the ice surface being reformed as we go along. If you wonder why we've got water on something that's so far away and so cold, this is due to a phenomenon called tidal heating, where essentially Jupiter's so big that it can create sort of tides that end up sort of moving things around, and that creates energy that can actually heat things up. If we look at things in a little bit more depth, a sort of cutaway model would look like this. Europa was sort of actually discovered in 1610. It's the smallest of the Galilean moons. It's got a diameter of about 3,000 kilometers. It's orbiting Jupiter in sort of 3.5 days. It's similar in mass to the Earth's moon, so it's not that far off, and it has an extremely low atmospheric pressure. And so when we look at this, the reason why people are interested in these ocean worlds is we have all of these things. We have an ocean. More importantly, this ocean connects with the sort of sea floor and the silicate. So this is essentially very, very much like what you would get on Earth in an ocean. And we'll come back to this later on, but the phenomenon that we want to be looking at more specifically, particularly for us in the context of astrobiology, is what we call hydrothermal vents. But I'll come back to this. I just wanted to point out that there are some hydrothermal vents. The other things that is really, really interesting is you might be able to see, depending on, I'm not sure whether the zoom quality on the video is good enough, but whether you can sort of see some cracks here in the ice and essentially some plume materials. So I'll sort of move on to this. What people have discovered, but again, this was discovered after the fact, is that every now and again, some big cracks open in the ice on Europa, and some water is being spewed out in the atmosphere and in outer space. It was essentially a sort of chance discovery in the Galileo mission data. So people sort of looked at things because some scientists have suggested that maybe there was some water plumes, some water jets, and they thought, oh, maybe it's worth looking. And this one is sort of quite a funny one, because what they ended up doing is they looked at some of the magnetic profile of what this moon looked like, and there was some sort of irregularities, and they try and fit a model, and the only model that would fit was if they had some sort of water vapor sort of around, and this is why it's got a bit of a weird shape here. This is sort of the simulated data, but this is important for two things. It indicates that obviously the ice moves and we have some sort of activity in the ocean, but also it means if we were to fly around Europa, which is one of the next planned mission from NASA, and we were able to fly through this, we'd be able to sample more or less what is in these oceans. We don't have any composition there because this was sort of magnetic measurements and various sort of remote data, but it's believed to be basically made out of salty water and surface dust. People have managed to see a bit of oxygen, a bit of hydrogen, which you'd expect if it was water, but that's pretty much where it stopped. So that was for Europa. If I now click, I'll go on to Ganymede. So Ganymede is the biggest of the Galilean satellites. And here it's got a the interesting thing with Ganymede is it has a magnetic field of its own, and we also think it's got saltwater underground ocean. So, but this one, it's interesting, but it's less interesting for the astrobiologists because the water is essentially insulated from the core. So what we want is to see the water interacting with the core. But here, there's not much. It's literally just water, ice, and some ice underneath. So it's one of these water sandwiches. Callisto, we talked about it earlier. It has an ice layer as well. That's the one where we're not quite sure what the core is doing, whether it's a mixture or not. It's still quite big, but it's a bit mysterious. I think when you actually look at Callisto, this is one of the ones where we have not much data on, and even the pictures, it's difficult to get actually reasonable pictures of that. The next interesting one, which is probably my favorite one, is the moon of Saturn. So this is Enceladus. Enceladus is wild. It doesn't look it, but it's a wild moon. So what happens is Enceladus is much, much smaller. So it's absolutely tiny compared to the Earth. But the nice thing about it is it's really nicely covered with ice. It has a very active ocean, and it has the advantage that it's been monitored very thoroughly by the Cassini mission. So we will see that it has sort of spray jets, and it has a region called tiger stripes. And I thought, when I found that out, I thought, well, you know, you not like something that has tiger stripes on it. It seems like, you know, it'd be the thing to do. So if we actually look a little bit at the statistics, so Enceladus was discovered in 1789 by Herschel. It's the 6th largest moon of Saturn, so not the biggest, but it's not the smallest either. It's very, very light. It's 680 times less than the Earth moon, but it has a sort of slightly more of an atmosphere, so 10 to minus 1 nanobars. So that's that works. That's sort of a reasonable type. It's not a great atmosphere to breathe in, but it's actually got a lot more. And if you can see, I don't know if you can see this sort of blue stripes at the bottom on the south pole of Enceladus. This is what people call the tiger stripe region. And the reason why people were very interested in that tiger stripe region is because in that tiger stripe region, there's lots of plumes, lots of spray. And so here what I've done, I've taken an old model from NASA, but I've recalibrated it for using sort of the geophysical model that was generated afterwards. So in this model, what we think at the minute is that Enceladus has an ocean that is 50 kilometers deep. If you think about it, 50 kilometers is probably about 4 to 5 times deeper than any ocean that we have on Earth. It's huge. It's got an ice shell that is about 20 kilometers. This is as thick as what you have on sort of Antarctica, etc., if not more. There are some places here where they think that in the tiger stripe region, the ice sort of thins out to slightly less than 5 kilometers. And this is why we think we've got some sort of plumes. Again, underneath, we think there are some hydrothermal vents. And those happen because the water is directly in contact with a sort of hot rocky core down there. So the plumes here are mainly concentrated in the south polar terrain. And the advantage here is that back then, Cassini actually went through the plumes. It was also one of these weird chance discovery because Cassini wasn't actually heading there to see any plumes. It just happened to fly through something. Luckily for the Cassini mission, this spacecraft was full of spectrometers, etc., and it had the spectrometers open and managed to essentially measure water, CO2, carbon monoxide, nitrogen, methane, and a few more things. That's for the good part. The bad part is the fact that the spectrometer, when they built it, was never meant to record anything that was very big. So there might have been some bigger molecules, but the spectrometer wouldn't have seen them. So we don't know whether there's some bigger things like maybe amino acids, maybe things that are possible life molecules. We don't know because it wasn't there. But the current sort of thinking, in particular, when we sort of look at some of the things that happen on Titan as well, is that the hydrothermal vents in contact with the water are able to generate or help generate some molecules that then would have got captured in the ice and got sort of spewed out into space. And so if we were able to go back with maybe slightly more sophisticated equipment, we'd be also able to analyze what happens in the ocean, which is a much better idea than some of the later ideas. I will show you some of the concept ideas that they have to try and explore the oceans over there. So I've talked a lot about hydrothermal vents, and I'm sort of initially, when I first started researching into this, I had to look it up. I mean, I had heard of hydrothermal vents because they're the sort of things that you have at the bottom of the ocean and on sort of lines. And the reason why everyone was excited when they heard about oceans in contact with not just ice, but with a silicate core, is that they know that on Earth, when that happens, we generate hydrothermal vents. So these hydrothermal vents are essentially places where you sort of, the water sort of reacts with the silicates and with maybe some of the magma that would be there, etc., and makes these plumes. So we have, they have sort of two types, they call them, there's a black smoker and a white smoker, so they generate some sort of plumes, and that in itself is interesting. But what is even more interesting is if you actually look, and there's sort of down in the picture, you can sort of see on both sides you have some fuzzy things, which is essentially the heat that comes. So we essentially have a sort of geothermal source, so this heats up the water. But more interestingly, on Earth, most of the geothermal vents are actually teeming with life. So there is lots of fish, crustaceans, funny weird animals that live in very deep water and at conditions where it's probably a bit more, some of them are a bit more acidic, some others are a bit more more basic than what you'd expect. So it was a bit unusual to find lots of life around here. But the reason why people are quite excited is hydrothermal vents in themselves provide first an energy source, but also are able to sort of generate some chemical reactions that would be probably just about right to create life forms. So then by that stage, okay, so we've got some moons that have a massive ocean, very deep, in contact with silicates. And if you put water in contact with silicates, you generate eventually hydrothermal vents. And on Earth, which is the only living model that we have, we know that when that happens, we have lots of life. So you can imagine how everyone just makes a very, very tiny step saying, oh, well, maybe, possibly, there could be life on some of these water worlds. We haven't seen anything yet. We don't know, but at least it has some right conditions. We'll come back to this later on. I wanted to tell you a bit more about Titan. I quite like Titan. It's one of the biggest moon, if not the biggest moon of Saturn. And it's sort of, Titan's a bit of a weird one. So Titan is quite in vogue at the minute because it's got this funny haze. I don't know if you can see, it's got a sort of thick, weird atmosphere that is made out, we think, mostly of sort of hydrocarbons and ice and dust. And it's sort of a bit like a big thick smog that you'd have on top of that. Here, according to the model, there would be a salty underground ocean in Titan. That would be sort of that sort of sandwich one, which would make Titan slightly less interesting if it wasn't for the fact that Titan has more or less a full chemistry lab on board. Titan is full of all sorts of random things and random molecules. So in particular, there is some good evidence that Titan, at least the atmosphere of Titan, generates some very complex organic molecules. And of course, when people suddenly say organic molecules, all the astrobiologists get really excited because, oh, organic molecules, we're made of organic molecules, so that must be really interesting. The thing that I thought was really funny when I looked at this diagram, which comes from our good friends at NASA, I like the fact that it has something that says mysterious growth regime, which I think is always quite funny. So over there's a big cloud where we don't really know how things happen, but we go from taking very simple molecules to make much, much bigger ones. And this is what they think creates this sort of haze that they have. The other thing that's really interesting is that picture over there that was taken by a Cassini mission. Here, this is the sun reflected, the sunlight is reflected off a hydrocarbon lake. So this is extremely cold hydrocarbon, think lake of petrol. And it is so huge that it can sort of reflect the sun off and you can actually sit over there. Titan is a really good and interesting place for all sorts of weird alternative life form type theories where people say, oh, well, what if instead of having water, we'd have just methane and we'd have a lake of methanes and various things. And could we make some life out of that? It would be very, very cold, but you never know. In fact, if you actually model things properly, Titan has many, many layers. It's a bit like an onion, where you'd have a rich sort of organic atmosphere, so an atmosphere that's full of really heavy molecules. We'll have a sort of outer shell that is water, ice, some subsurface ocean, which is quite salty, then a high pressure ice, and then a sort of hydrosilicate core. So this is sort of a silicate core with, so it's sort of sand and ice and water all mixed together. So this is sort of what we think Titan looks like with its sort of many layers, which makes it really, really interesting. So we've been now in the outer solar system. We've seen what happens around Jupiter. We've seen what happens around Saturn, but what's happened in the inner solar system? Why do we only have one water world, which is us, and where does everything go? So the current theories suggest the following. So Venus, we think, had possibly an ocean, and this is what it would have looked like at the time. But essentially, it boiled off. So what people have done recently is that they used the climate model that they have for doing Earth climate modeling, and they thought, well, they took some measurements from Venus and said, well, can we reproduce what we see and sort of wind back the clock? So what they did when they did this is they found that for up to sort of 2 billion years after it was created, and it sort of was there. It had liquid water, not very much, but a shallow liquid sort of ocean, and actually even reasonable temperatures. Venus is usually called the Earth's evil hot twin, because a lot of the composition on Venus looked like it's got a similar makeup to the Earth. But what happened is the sun is much, much closer. So Venus is really very much closer to the sun. And that eventually caused all the water to evaporate. Not only that, but because it was really bombarded by lots of sun rays, it actually managed to even break down the water molecules. So the water molecules got broken down, and that then generated big CO2 buildup. And if this sounds familiar, this is basically what's slowly happening here as well. So the large CO2 buildup essentially created a massive greenhouse effect that then heated things up even more, and the water evaporated even more, and broke down, and eventually created the horrible conditions that you have now on Venus, with probably not very much water left. So that sort of explains Venus. Mercury, we don't even talk about it because I don't think there was really very much there. Mars is an interesting one. So Mars, we talk about Mars's lost ocean. So Mars, if you actually look at some of the pictures from the Mars rovers, they look very, very, very much like some of the terrain that you would see in rivers. So you will see some channels, etc. I know that so one of the people that I work with in Hull that looks at seabed formation is also analyzing Mars data to try and work out what the seabed would have looked like. And this is not from him here, this is some work that was done by NASA. But what they managed to do is they looked at the ice cap, and there's still some polar ice cap. You can see a little bit of it here at the top on Mars. And they worked out, based on what was left and the ratio of different types of water that you get on the ice cap, they worked out that at the time, so 4.3 billion years ago, Mars would have probably been half covered with water. So it would have had an ocean that was probably taking sort of half of its surface, and it lost about 87% of water over time. So essentially, this is mainly due to loss of its atmosphere and the magnetosphere that it has, that is essentially slowly going away, and that led to the ocean is essentially being lost and evaporating there. Essentially, what's interesting is the magnetic side of all these planets and moons is quite important in order to maintain things. We said right at, not quite at the start, but early on, that a lot of these ocean worlds are living near very big planets. That is also helping sort of shielding things a little bit and making things probably much more comfortable for those. This is why probably anything that is close in the sort of inner solar system will really struggle with some of these things. For a bit of trivia, we have Ceres here, which is just sitting in the asteroid belt. That one's a bit of a mixture here. People think that it's sort of, the water here sort of sucked in, and it's got loads of salt. So we've got salt deposits on Ceres. You can sort of see these little white spots that people thought was ice at one stage. They end up being some sort of salt. So we think it had a sort of brownish type liquid that maybe evaporated or has gone slowly from Ceres over time. Ceres probably got a bit of a rough ride anyway, because it's not really, it's in the middle of other asteroids. All sort of random things might happen to it. So it's maybe not quite as typical of an ocean world as we would really understand it. But there's a lot more interest now on this for this moon, because And this is the sort of the Dawn spacecraft that is now sort of completing a mission on Ceres and try to sort of find a few more things about this dwarf planet. So here is essentially that was a catalogue from 2016 of all the ocean worlds. The ones in blue are the confirmed ones, so the ones where we know for, let's say, 99.9% that this is definitely got water on it. The others are all suggested. Mimas, Triton, and Pluto are sort of the next one that people are thinking, this is sort of getting quite confirmed. We have, well, the Earth's moon. Well, there's a bit of ice on that, but there's no ocean. Here we've got a lava ocean. Some of the others, you know, not entirely sure. But the main next candidates would be the ones that I've circled here in red. If we talk of future, I don't know why I realize I put ocean world, so apology for that. If you go then further out, of course, there's loads of exoplanets. Exoplanets also have potentially loads of water on them. There's no reason why not. Some of them might be really big. So here, this is sort of a collection of the ones from the Kepler mission and some from the TRAPPIST system that are Earth-like. And the reason why they are Earth-like is that they have probably a composition that's not too far off ours. They're probably sometimes a bit bigger, but they also have water, and a lot of those can also be ocean world. It's harder to confirm those, but it's still a possibility. So there's probably a lot more water worlds than what we thought initially, in particular keeping in mind the fact that people have really started to understand what happens in water worlds for the past sort of 20 years. So why the interest? The interest, apart from, I thought I'll show you probably a ridiculously bad picture of Jupiter and its satellite that I took from my back garden. But I just think it's wonderful. So essentially, all of the moons I've talked to you about are somewhere in that picture. Well, at least the ones around Jupiter, and so we can see some sort of interesting thing. The interest is really around potential life in the universe. So if we move to what we know about how life can be generated and how life sort of works, the problem that we have at the minute is we can only work with what we know, which is life on Earth. Life on Earth is usually generated using carbon mainly, and usually people will then talk about amino acids and proteins, DNA, etc., etc. And so if you actually wanted to make a sort of quick recipe of what you need to generate life, the first thing that you're going to need is water. We'll see in a minute why, but you'll need water, ammonia, methane, carbon, some aromatic molecules, some sulfur oxides. And then you start sort of thinking, well, what is a life form then? What would be a life form? So probably, if we're really lucky, we maybe possibly think that we might see something like those green things. They're not really green. This is just some sort of bacteria that you might. So if people found extraterrestrial bacteria, we would all be ecstatic. That would be amazing. But you know, it's probably not even guaranteed that we'd find something like that. But a real issue, once we've sort of decided, well, what a life form, and there's loads of questions around what we define as a life form, etc., etc. We could go into those later on if you want. The real issue is, where can we find those, and what sort of science should we be looking for? And here, one of the interesting things is most of these things won't happen without water, mainly because water is what we call life solvent of choice. If you actually think of water, it has some properties that other liquids don't have. The first one is it's liquid below 100 degrees. If you actually go around and look at liquids, there's not that many that won't kill you and won't necessarily be toxic that are liquid below 100 degrees. In particular, if they're simple to make. So the next one that would be simple to make would be hydrogen sulfide, which is H2S. That's something that is only liquid below -60 degrees. So it's fine. You're in space, you could go at low temperature, but it's not necessarily the best. The other thing that's really interesting is water is one of the very few liquids where its solid is less dense than its liquid. So what happens is it actually provides an insulation in ocean. So when you actually put water and it freezes at the top, it enables you to insulate this from the cold. Finally, another, I mean, water has loads of other properties. I just chose 3 that I liked. The third one that I find is quite interesting is the fact that water molecules want to stick to each other. They don't really want to stick to anything else. They're just like themselves. And they stick together quite strongly, but actually they're not too stubborn, so that this can be reversible. They can unstick themselves. But what happens is it means that if you put oil and water, you can generate, you know, a sort of membrane. So you can have oil and water separate. And this is essentially the whole mechanism that goes around cell membrane formation, etc., etc. So without water, you won't have any of these 3 key properties that you need to make life. And so if you move this a bit forward, you could look at what people call the keystones of habitability. And you can start putting some of these planets on a Venn diagram. I thought I had to have a Venn diagram. I'm, you know, working at Hull. Venn was from Hull. I can't do a talk without a Venn diagram. So I got a Venn diagram. And if I put together things that you need. So you need the water, but also you also need the elements. So you need to have the raw materials to do things. And you need also energy to do things. So if you actually look at water, there's MSAS, Triton, maybe Ganymede, Callisto, Pluto, question mark, Europa, Enceladus, and Titan. The ones that have the right sort of composition are in there. MSAS and Triton are probably not in. And if you actually then start to look for energy, so this is hydrothermal activity, or etc., which would then be the sort of things that you would need to actually make things happen. You're then down to those 3, Europa, Enceladus, and Titan. So by actually saying, well, I'm going to need this and this and this and this, you suddenly start really thinning out the places where you're more likely to find life. Now, the thing to keep in mind is this does not mean that other things might not happen on the other planets. It just means that life as we know it, and with the elements that we know are supposed to be there, probably only happens only on sort of Europa and Enceladus, Titan. Maybe, maybe not. And so at the minute, the way sort of this is a graph that was showing how far along we are with exploring these various worlds. So, for example, Voyager 1 and 2 looked at Europa, Enceladus, Titan, Ganymede, Triton, Callisto. Then we had the Galileo mission that looked at some of those, Cassini, Huygens probe that went on Titan, New Horizon here, and a Galileo that went to Callisto. And so here, this is essentially the sort of blueprint that NASA has for the sort of mission that it's going to launch, try and explore some of these things. So they have funny names. We have the Europa Clipper. We have JUICE, which is based around some of the Jupiter objects. We've got Dragonfly. Dragonfly is a brilliant program where they're sort of trying to think of landing a sort of helicopter on Titan. And here they're looking at landers, etc., and direct exploration of subsurface oceans. So we still need quite a lot of data. The other thing that we have is, if you actually look at the top, there are sort of things where you have water, element, energy, time, which is how long these sort of oceans have been there. And you see that there's not that many that tick all the boxes. And this is why for example, Europa was chosen as the prime target to go for exploration, really, because that's probably the one that ticks all the boxes at the minute. Personally, my personal favorite still remains Enceladus, mainly because in Enceladus, we actually have some data that show we had water and organics and things like that all through these various plume in the ocean. So Cassini actually did fly through the plume, not like Europa, where we sort of worked out some plumes afterwards. And we could see that there were some really interesting traces of organic compounds and things that make things, make lots of biological molecules. So I think I've probably talked for long enough. I'm going to just give you some conclusions. The image in the background is one of the concept things. So the next thing that they're planning to do eventually is to actually go and land a submarine in there, because you would, right? If you've got a huge ocean, the best way to explore an ocean is to go in a submarine. Of course you would. I have no idea how they're going to manage that, but that's sort of, at least I'm not in working with any of those missions yet. But if they do get a submarine on one of those, I'll go. So anyway, I think that the sort of three main take-home things that I would sort of like to leave you with is the fact that these ocean worlds are really a key part of understanding how life evolves in the universe, because without water, you really struggle to do a lot of the chemistry that we need for life. Second point is that ocean worlds are much more common than we initially thought. We suggested that maybe they might exist, but actually they are really much more common. But it's still a very young area of research, so things are still a little bit fluid. Things change quite a bit. People revise the numbers quite quickly, so it's not quite as set in stone as some of the usual things that we have in astrophysics and astrochemistry. And the nice thing about that is, because it's still new, most of the future exploration missions are really going to provide really interesting, vital clues on what happens on these worlds. Even if we end up, we're not going to Enceladus, but we go somewhere else and you find more data, most of those will be really, really useful. And with this, I think I will take some questions, but probably by now I should stop sharing screen, and then I'll reshare it as and when. And you can mute me now for a bit.
Thank you very much, David. That was an incredibly interesting talk.
Thank you.
What we do is that I will ask people for questions and ask them to either put a digital hand up or to wave at me, and I'll try and spot them. And then I'll nominate them, and so we don't have an overall clamour and get lost in the feedback, etc. Just a question myself. Could you just explain the difference again between a tetragonal ice and hexagonal ice?
Right. Okay. So this is, I'm going to try and see whether I have what I can do. So I'm going to just show you what I've got on my screen there, which is this one here. So what happens with ice is that the water molecules can essentially arrange themselves in loads of different ways. If you think of a water molecule is a little bit like, I think of it a bit like a hand with two prongs like this, and so it's sort of connecting with each other. And depending on the way that they arrange themselves, they form what we call different types of ice. In itself, not a problem, it's just different ways of arranging themselves. But what happens is different types of ice have different properties. So ice 5 or 6, which is, if you can see the diagram, I'm hoping you can see the diagram, is sort of around here. This is a type of ice that only exists at about 1 gigapascal. So that's at huge pressure. And so essentially what happens, you can imagine taking an ice cube and squishing it mercilessly on all sides. And essentially what's going to happen is the molecules are going to be forced together, and they're going to have to find essentially a way of existing while being really, really squashed. And what happens then is they rearrange themselves to form essentially a much more compact ice, which is why it's denser. And we call that ice 5 or ice 6, etc., etc.
Okay, thank you. So I'm not going to get any my gin and tonic very soon.
No. But I think probably if you got it in your gin and tonic, it'd go at the bottom, which would be really funny.
It should stop my top lip getting cold while I'm drinking gin and tonic.
That's for sure. That's for sure.
Okay, so has anybody got a question? Peter.
Hi. It's not so much a question, but more of a point of discussion. Mars seems to be looked at like, for example, a second Earth, and how long it was habitable. But actually, it seems that Venus is more of a better candidate. It seems that Venus remained habitable for far longer than Mars. I read an article, I don't have the reference here, that actually it remained habitable for up to just about 700 million years ago. A bit longer than the paper that you quoted. I don't have the reference mentioned. And there's another point I'd like to mention, that there's a faint sun model. So a lot of people, or scientists, are trying to work out how Mars had what it did with the sun being far fainter than what it is now. So.
Yeah. Oh yeah, I think, I mean, this is the thing. When you look at some of these sort of explanation for Mars and Venus, you're nearly talking about people doing a sort of remote archaeology in some ways, because you're sort of saying, okay, you're talking a really long time ago, and they look at the things. To be fair, I think to the scientists, the ideas that they have are actually really clever. So the way, for example, they worked out the amount of water that there was on Mars is actually really, really, really nice. It's a really nice idea. But I think a bit like everything, I'm not also entirely sure, you know, there's no way of proving it. You don't know. These are just, you know, models that they have. The same, you could also even go one step further and say a lot of the models, for example, that people use to fit the data that we have on some of these satellites, you know, you could change a parameter a little bit, and suddenly instead of having, you know, 50 kilometers of ice and 20 of water, you have 100 of water and 3 of ice. So it's really, a lot of it is, you know, still needs a lot of cross-examination. But I think at the same time, it's really interesting to think, for example, that, you know, Mars did have some water, same as Venus. When at the minute, when you see the images from the rover on Mars, you think, gosh, this looks really, really, really dry. But interestingly, with the channels, which is interesting as well.
I often think it would have been fascinating to go back billions of years ago and see 3 potential Earths in our solar system, you know, and something like that.
Yeah.
We've all gone their separate ways.
Yeah, that's right, yes.
Thank you, Peter. Has anybody else got a question? I don't see anybody waving at me. Oh, Tony Morris, can you unmute your...
I'm unmuted, Paul.
Thank you.
David, when we talk about the classical habitable zone, most of the water bodies that you've discussed tonight are outside the classical zone. Would you expect the classical zone to be kind of expanded as more knowledge gets about where the water lies?
That's sort of an interesting, it is actually quite an interesting point. I think, so when you think about habitable zones, you have a margin of error. I think there's definitely that. But I think, at least for us, from say a chemical point of view, from an astrochemistry point of view, you also need to have the extra ingredients. So I would probably say it's habitable zone plus all the other stuff that you need in order for things to work, which I think explains probably why Earth works the way it does. And I'm not really expecting to find anything in any of these oceans. it'd be great if we did, but you know, we're quite far away. It's really not, you know, temperature wise, etc. It's all very different. So it's probably something where you have to have a combination of things. And so I worked with someone who did you had Brad Gibson a few was it last week that Brad
last week, yes.
Last week. Well, Brad works quite a lot on determining habitable zones and things like that. And I think he'll be the first one to say, well, you know, it's within a few parsecs or something like that. So there is that sort of margin of error. But for me, from sort of a, you know, if I take a sort of put a real chemist or biologist hat on, I'm going to say yes, but you know, even if you're in the right zone, you also need all the ingredients for it to work. So I would see those as more extra thing to put on the habitable zone.
Okay, but isn't that an Earth-centric view?
So, yes, but I guess at the same time, the issue we have is it's hard to know how else it would work, because Earth is the only one where we can demonstrate life. And I think that's really the difficult bit about it, because you could say, for example, there was a lot of discussion at one stage about silicon life, saying, oh, you could do more or less the same thing with silicon that you can do with carbon, except that if we've got any chemists in the audience, if you try and bubble, you know, methane in water or silicon H4 in water, you'll know the difference. One of them explodes in your face, the other one just bubbles quietly. So there are some really interesting concerns. And if you actually look at the way things work out, there's a very, very subtle balance between sort of the forces, the bond strength, the various things that make probably carbon a very, very, very likely candidate to generate life than, say, silicon or other things. But this is also where Titan becomes really extremely interesting, because Titan, I was telling you, there's loads of really weird lakes of stuff that they have. And there you could sort of start thinking, well, actually, so there's some colleagues that have done, some colleagues in the US that have made experiments where they generated rocks out of hydrocarbons. And they were basically a bit like taking some diesel into a big nice rock, and they could calculate the properties of these rocks. It's amazing. So you could generate an entire new set of things on different planets. But I think, unfortunately, probably, most of the time you do end up going back to a sort of a very Earth-centric view in some ways, because you end up saying, well, okay, there's all these maybe, and you sort of have to say, okay, right, we can imagine all sorts of things, but first, maybe let's look for the things that we know work. And then, you know, but I completely agree. It's always very Earth-centric, and it's a bit annoying in some ways, because it'd be nice to have other things, but it's difficult. I think people do try to find different ways of making life, etc., but it's difficult.
Just to carry on that point, one of the things I noticed in some of the data that you were putting out about the spectroscopic finding was that there wasn't very much evidence of free oxygen. It always seemed to be bound up with hydrogen in water or carbon in carbon dioxide, but it's incredibly important in our model of life to have that level of free oxygen.
That's right. So a lot of the oxygen that they have there is really then, you know, because essentially for us, for oxygen, we're talking about essentially an atmosphere of oxygen where we could breathe. A lot of the moons I've shown you have extremely thin atmospheres. You know, they're very, very small, very low pressure. So it's difficult to know whether you would have something that would work with only dissolved oxygen. So if you think of some of the fishes and things that you would have sort of in quite deep sea, some of those will be able to absorb some of the dissolved oxygen. I think it's not that there's necessarily no oxygen at all. I was sort of trying to look back at the spectra that we have. You'd expect sort of a peak around 32 for oxygen, but some of those sometimes will be masqueraded with other molecules as well. There's definitely oxygen. It's not absent from the thing, but often it is used and included in other things. The main one is to make water.
Yeah. Okay. Tony, have you got a follow-up question?
No, thank you.
Okay. So, Peter Lloyd, can I ask you to unmute yourself, please?
Yes, thank you, Paul. I just wanted to make a comment on the idea that there might be molecular oxygen lying around in the universe. I think one tends to get a bit blasé about the reactivity of oxygen.
Yeah.
We have to remember that oxygen is probably the second most reactive element known, and the chances of it surviving in its pure form out in the wild, as it were, is extremely unlikely, and that it exists on Earth simply because it's being generated so consistently.
It's
that was a lesson that the Apollo 1 astronauts learned to their cost.
Yeah, it's a very good point.
Okay, I'm looking around for any other questions. Roy Gunson, can we come back to you? Are you stable now?
I think so. I think part of it got answered while from Gary's. I think it was Gary's question. I mean, when I was making the comment was that I've read the report somewhere in an article that the inner planets are lucky to have water, and that if we go out in the universe into these extrasolar planetary systems, that we're likely to find the water world out past the end of the Goldilocks zone, locked in very deep oceans under an ice crust, because the inner planets, where the Goldilocks zone is, early in the development of the system, when there was a protoplanetary disk, the water would have got pushed out to these outer regions of the planetary systems.
Yeah.
Okay.
That was what I was going to say.
Okay. Fair enough. Has anybody got any other questions?
I think there's a question on the chat, I think, which was, is it possible to conceive of living system based on methane rather than water, for example, on Titan, which is really interesting. This would be really good. This would be really good. It's one of these things, and I think this is why I had that slide about the useful properties of water, that methane somehow doesn't quite do the same thing as water in terms of, even if you get it as a liquid, even if you imagine, okay, it's cold, it's fine, it's not, it does different things. So often there will be things that people haven't really looked at. So we don't really know whether you can live in, in a lake of methane. I don't know. You probably, maybe it's a good idea, maybe not. It doesn't capture things the same way. So the water is quite good at capturing oxygen and gases, etc. You can dissolve things a little bit in methane, maybe not quite as much. This is very, very much one of the things that people are very excited about in Titan. So I think it was probably about a year ago when I was talking to some of the scientists from NASA that work on the Titan missions. They seem to be excited about absolutely everything. Any molecule that seemed like it would work with methane, they'd be like, yeah, we'll have that. We want some data on this, we want some data on that. So I think everyone's keeping very much an open mind. The real issue that we'd have with finding a living system that would work with methane rather than water is the issue of making sure that we would recognize that this is a living system or not, because it might be very, very different and we might not know. It might just be something that looks a bit like a rock that happens to be doing something on an extremely slow timescale, and we might just miss it.
That is a point to ponder. What do we actually mean by life? And you know, I think that's a completely different talk.
Definitely,
yeah, and we'll give you a few months to get that one ready, David.
Thank you.
And then you can come back to us. Can we give a big Mexborough and Swinton Astronomical Society thank you to David?
Thank you.